Here's an example of polar graphing aided by calculus. We're looking at r equals sine 3 theta. And this is the graph that the computer provided. And I want to understand that and be able to know how to reproduce that by hand. Not with the intention of pretending the computer doesn't exist or the calculator doesn't exist, but with the idea that we wouldn't really understand it if we can't reproduce it, at least a simple graph like this by hand. The most important thing to note, let me look at another version of this that I can draw on by hand, is just what is the process of polar graphing? What's a good way to think about it? And this is especially important if you want to also think about calculating areas inside polar graphs, things like that, stuff that happens in like a BC calculus or multivariable calculus class. The way I like to think about it is that we've got a radar station right at the origin, and there's a radar beam that sweeps continuously around in various directions. And so it starts out going maybe very close to the x-axis, and then it's sweeping counterclockwise because that's the positive direction. And at each different angle, that's a different value of theta, it detects how far away the curve is. That's the value of r. So this metaphor gives you an idea, a way to think about changing the theta progressively, that's the radar beam sweeping around, and seeing the resulting different r's. And that's the usual way we have a polar graph, is that usually theta is the input and r is the output. Now that can get a little weird when we use this funky convention that theta can be negative, and that r can be negative, and that when r is negative everything is reversed, and instead of going in a certain direction you go in the reverse direction. But still, the basic idea here is that we're sweeping around a radar beam and figuring out where in that direction, how far do we go out in that particular direction to find the curve. And that idea also gives us an idea about how we might want to split up this region if we're going to find the area of it or integrate a function over it, for example, in a multivariable calculus situation. So let's look at some of the features that this function has. The first thing to look at is symmetries. Let's make this a little bigger. Okay, the graph does seem to have some symmetries, and there's a lot of symmetry here. What we always look for in symmetries is mess with the input and see what happens to the output. Well, we have that if theta gets changed to pi minus theta, then what happens to r? Well, let's see. The new r for this new theta would be sine of 3 times pi minus theta, equals sine of, let's play with that a little bit, that's not a 2, that's 3. Okay, sine of 3 pi minus something. Well, we can always take out a 2 pi. Because that doesn't change anything. It's periodic with period 2 pi. And now sine of pi minus something, that's exactly the same as the sine of that something. That's one of our basic, that's one of our basic rules about the sine. And so what does this say? Well, why would we do this theta to pi minus theta business anyway? That talks about flipping across the y-axis. If this is theta, then pi minus theta means go around to pi and then go back by the same amount theta. So this investigates what would happen if I try to flip around the y-axis. Well, if the r changed, it might not be flipping around the y-axis at all. It might be something different. But in this case, the new r, which was sine of 3 times the new theta, is the same as the old r. So old r. And so that means that if I put the radar beam out in a certain direction over here, I get a certain r. If I put the radar beam in this direction, I get the same exact r. That means it is going to be symmetric about the y-axis. Okay. There's some other symmetries we can investigate. But I don't want to go through every single one of them in the interest of a short video. The one I really want to mention, though, is this 3. What kind of influence does that have? And the fact that sine is periodic. Well, we know that if I added 2 pi to the thing that's inside of the sine function, let's put parentheses in here to emphasize it. If I can manage to add 2 pi to this whole quantity, the sign won't change, and so the radius won't change. It's kind of like I took a 2 pi out of here. So what would I add to theta in order for 3 theta to go up by 2 pi? Let's see. Let's take theta and replace it with theta plus 2 pi over 3. And then the new r is going to be sine 3 times theta plus 2 pi over 3. Okay, so that's sine of, as expected, 3 theta plus 2 pi. And that's going to be just the same as sine of 3 theta. And that is the old r. So we've got something where if I crank around by 1/3 of a full revolution, the radius doesn't change. So whatever angle, whatever radius I get when I sweep the radar beam out here, if I crank that around by 1/3 of a revolution to get over to here, I get the same r. That's why it has these 3 leaves. We can combine that to get basically all the symmetry that this shape has. So the y-axis symmetry tells us that you're going to have these 2 equal shapes left and right, and then it's also going to have something down here as well, and that guy's going to be symmetrical across the y-axis. Well, but this lobe, it was the same as this lobe was the same as this lobe, so that's why you get these 3 symmetrical lobes. So we don't know, just from this analysis, we don't yet know exactly what those shapes are. We don't know that they're these simple leaves, but we do expect this kind of symmetry where we're going to have 3 pieces, but each of the pieces has some symmetry as well. Okay, so combining all this, we really don't have to graph that many different values of theta. If we wanted to, we could just do like this first quadrant, flip it over, start to see that picture, and then just see that we can rotate it to get the whole thing. So what else do we want to do? So symmetries is a really important one, and then the max and min are really important. What happens, what's the biggest r can be, what's the smallest r can be, can it be positive or negative? That's very significant. So let's just make a real simple sign chart for this function. Let's make a little table. I probably don't need that many rows, but that's okay. Okay, so various values of theta and then sine information. Oops. Sine of r. So let's just figure out the sine first. So if theta is between 0 and when is r going to become it's going to start out being positive because sine 3 theta, back up to here, sine 3 theta, if theta is a small positive number, then 3 theta is going to be small and positive. It's going to start out being positive. It's going to stay positive until 3 theta is equal to pi, or theta is pi over 3. So and then it's going to, so that's going to be plus. Then pi over 3, oh, you know what? I'm really going to take advantage of this symmetry. As I said, I really don't have to do more than the first quadrant, then we can figure out the rest from the symmetry. So I'm going to blank out all these entries. Do it real quick. Theta going up to pi over 2, and that's not because it has to stop at pi over 2, it's because I can stop at pi over 2 to do one quadrant. In there, 3 theta is between pi and 3 pi over 2, and so the sign is going to be minus. Okay, and of course it's going to be 0 right when theta is equal to pi over 3. And let's write that down. Sine, let's see, if theta equals 0 or theta equals pi over 3. Then r equals 0. This is super important where r equals 0. Of course, it's obviously an interesting thing about, it's like somewhat analogous to like an x-intercept, but it's actually even more interesting than that for polar coordinates. Something very special about polar, that the fact that we know the theta values that give r equals 0 not only tells us that it does go through the origin, it tells us how it goes through the origin. It tells us that as the radar beam sweeps, like to pi over 3 for example, as the radar beam is sweeping from pi over 6, pi over 4 up to pi over 3, that's the direction the radar beam is in when this object that's being tracked by the radar comes in and slices through the origin. So what that means is that it actually tells us the direction in which it comes into the origin. From a calculus point of view, that's a little strange, because direction information usually needs a derivative to calculate. But the one place you don't need that is polar coordinates going through the origin. Just by calculating the function and knowing where the function itself is 0, not the derivative, you actually know some direction information, how it slices through the origin. It's a very special thing about polar. So it tells us that there's going to be a part of the curve tangent to theta equals 0, which is this guy, tangent to the x-axis, and a part of the curve tangent to theta equals pi over 3, 60 degrees, that slices through the origin. So it also tells us that when theta is between 0 and pi over 3, we expect to get plots over here somewhere. We don't know exactly what the shape is quite yet, but we expect, since r is positive between 0 and pi over 3, that's why we get this lobe here. And then the negative, remember, the radar beam is shooting up between pi over 3 and pi over 2, up in this region. It doesn't see anything in the forward direction, but its magical backwards radar sees this stuff with the negative r. Now all we need to do is look at the maximum value. So when is r at its maximum? Well, in general we need to use calculus for that, but this is not a hard function. Remember, this is r is sine of 3 theta. We know where sine achieves its maximum. This is going to be when 3 theta is equal pi over 2, and that's when theta is equal to pi over 6. And so, not surprisingly, halfway in terms of angle between where it starts the lobe and where it comes down and ends the lobe and crosses back to negative, you've got this maximum value, pi over 6. So to plot a fairly decent plot of this curve, all you need to do is plot that one point, theta equals pi over 6 and r equals 1, because that's sine pi over 2. Plot one unit out in the pi over 6 or 30 degree direction, and then just start out from the origin and smoothly go out, out, out to that guy. Then come back to the origin and make sure you come in along a 60 degree line. And then, let's see, there's one other thing we need to know. What's the minimum value of r? Okay, when is r at its minimum, that is, its most negative? The answer won't be too surprising, especially since we've been staring at the graph for so long. R equals sine 3 theta. So that's when we want the sine to be minus 1. That's when 3 theta is 3 pi over 2. And that's when theta is pi over 2. Okay, that makes sense with the graph, because when theta is pi over 2, the radar beam is trying to shoot straight up, but when r is minus 1, it's going to record this point that's backwards by 1. So we just have basically these 2 points to plot. That's the biggest r positive, that's the biggest r negative, and then 2 lines to plot, just this line and the tangent line this way. And if you just start out tangent to that first line, theta equals 0, go to this point, come in tangent to pi over 3, go smoothly out to that point. And then what have we got? We've got already 1.5 of the lobes, and then you just flip it over the y-axis and you're actually done. We didn't actually even really have to use the threefold symmetry, although it's an incredibly good thing to know about to confirm that this is really the right picture. When this guy gets flipped over, we create this whole lobe. When this half lobe gets flipped over, we create this half lobe here. If we had been really fancy about the symmetry, we could have actually deduced just from this 1/2 of one lobe, probably, to get the rest. But we would have had to been a little bit more sophisticated about analyzing the symmetry. Okay, so again, look for zeros of r. They're crucial. They give direction information to the origin. Look for max and min of r. Look for symmetries. That's a lot of good tools. It's not every tool possible, but it's a lot of good tools.